All right, so now we're going to look at an impulse turbine problem. Remember, before we start, this page here, this note that I made for you guys, very important. You need to memorize this page. You need to be familiar with the different types of turbines: impulse turbine, reaction turbine, which we're not going to do. Um, and what it means if the steam is discharged axially, all right, which means that this angle here, beta, is going to be at 90 degrees. All right, so you need to learn that. Um, yeah, so that's the angle which the steam leaves the turbine. All right, the turbine blade. So you need to know that. It's very important. And then also over here you need to know this. So here it's speaking about the different angles. You need to know what is alpha, which is the nozzle angle. What is beta? It's the angle that the steam leaves the blade, right? Um, what is u, right? Okay, that's not an angle, but that is the velocity of the blade. Okay, that it's moving at. That's the speed at which the blade is moving. What is theta? What is phi? All right, there it shows you there the inlet blade angle, the outlet blade angle, and then you need to know these different velocities. All right, so all of that you must really commit that to memory. Otherwise, if you don't, you'll suffer with this forever. All right, so you should do it now ahead of the next level, because at the next level we're going to do a multi-stage turbine where there's two sets of rotating blades and a set of stationary blades in the middle. All right, but forget that for now. For now, you need to memorize this. All right, so here's the problem we're going to look at now. It says here the velocity of steam leaving the nozzle of the impulse turbine is 900 meters per second. Remember, there's the rotating blades there, the blade ring, and that's what's rotating, and the steam is like shooting in there, right, through a nozzle, and it comes at a certain velocity and at a certain angle, right? So they tell us now that that velocity of that steam coming in here is 900 meters per second, all right? And they tell us what the angle is as well, all right? So they say that angle is 20 degrees, okay, not degree C like I wrote there, sorry. The blade velocity is 300 meters per second, okay? So if you look at the diagram again, what is the blade velocity? It's these blades that are spinning, okay? 300 meters per second, right? So it's spinning, okay? And it says then the velocity coefficient of friction is 0.7. Remember now, these blades, they have friction. So when the steam moves across the blade, this is just one of the blades, it loses some of its velocity because of friction. All right, so it comes in at a certain velocity and it leaves at a slower velocity, right? So we have to take that into account. And then they say in the question it's 0.7. And then they say that the blading is symmetrical. Okay, what does that mean? Okay, so that, they don't always say that, but in this case they do. And that's a very nice thing, because when it's symmetrical, it means that the angle of the inlet of the blade is the same as the angle of the outlet of the blade. Okay, so if we know that angle, we know that angle as well. Okay, so they say it's symmetrical. And then they say the mass flow of the steam is 1 kilogram per second. All right. Then, very important before we begin, the scale. They give us the scale, which is great. 1 centimeter equals 50 meters per second. Okay. So we need to use that scale. Okay. And then we're going to answer these problems afterwards. Right. So first of all, let's see here. We can write down the information. Okay, so let me use this page here to write this information down. So they say that our V1, let's see here, V1, which is the velocity that the steam is coming in, that's 900 meters per second. Okay, then they say that the speed of the blades, or the velocity of the moving blades, is 300 meters per second. They say the mass flow is 1 kilogram per second. They say that the angle of the steam that's coming in, that angle is 20 degrees. Then they say that the coefficient of friction is 0.7. Okay, and then they also say that the blading is symmetrical. Okay, so therefore theta equals phi. Okay, remember that on the blade, eh? So there's theta, the inlet, and there's phi at the outlet. Okay, so that's all cool. Now we can start drawing this thing. So before we begin, the easiest place to start in this situation is with the speed of the rotating blades. So we can start off over here. And they said that the speed of that blade is 300 meters per second. Okay, so what we're going to do is we have to use the scale. Okay, so on our calculator, we have to say 300. So we got 300 meters per second there. And we're going to divide that by the scale of 50 meters per second equals 1 centimeter. So it means we have to make that line 6 centimeters long. Okay, so here we go. So the first one goes 6 centimeters. Right, there we go. So there's the first line. And then we can say here that U is 300 meters per second. Right, and that is also our length is 6 centimeters. All right, so that's our first line. Okay, then we have that. Now we have to put in now the speed of the steam entering. All right, so that is, they said, 900 meters per second at an angle of 20 degrees. Okay, so we're going to go on this point. Now this is where it comes. You have to learn how to do the diagram. At that point there, that's where the steam is coming in. All right, so we're going to use our protractor now, and we're going to measure off. So we put it on that point there where it comes in, and we're going to measure off 20 degrees. Okay, so here we go. Here's 20 degrees, like that. So from 0 to there is 20 degrees. And then we make a construction line. So from that point to that point, there's the construction line now. Okay, and then how long must we make it? Okay, so we need to know how long. So we know now what phi is. So we're going to say phi is alpha. So then on a calculator, we can say 900 meters per second divided by the scale, which is 50. And then it means that that line is going to be 18 centimeters long. Okay, 18 centimeters long. So we're going to measure off here along that faint line. We're going to measure 18. It goes right off my page. So we're going to say 18 centimeters. And there we have it, 18 centimeters. And there's the first line. So now that's going to be 900. So that's V1, which is our velocity of our steam coming in, 900 meters per second. And that length is 18 centimeters. See that? All right. Now it gets quite easy, because now on this side here, remember this side over here has got to do with the angle of the blade, the inlet and outlet blade angles. Okay, so now we can just say we're going to join that line or that end to that end. Okay, so that we can get the relative velocity. Okay, I'm going to do that in blue so you can see it nicely. There you go. All right, so there you go. That's that. And that line now is the V1 or V relative velocity 1. Okay, VR1. And we don't know how long that is yet, but what we can do is we measure it now. And what am I going to get there? I'm getting like 12.5 centimeters. Okay, 12.5 centimeters. So I'm going to write here 12.5 centimeters, and I just times that by the scale. So 12.5 times 50, and then I know what the velocity is now. Okay, so that's 625 meters per second. That's the relative velocity. So the incoming steam relative to the moving blade is that. Okay, so that's what that is. Okay, and then we're going to do the angle quickly. Okay, so now that angle is going to be our theta. Okay, so that's the inlet angle. All right, and then because we said, or the question said that the inlet angle is symmetrical to the outlet angle, then obviously the outlet angle, which is phi, is going to be the same as that. Okay, so now we have to measure that. So we have to take a measurement. So remember, we take the protractor, we put it on that point. There we go. And then we measure from 0, and we see here that the angle is about 29, say about 29 degrees. Okay, so I'm going to just say 29 degrees. So that angle is 29 degrees. Okay, and then you see, so we measured for that one, we went like that, right? And then on the outlet, we're going to measure from this side here. So we're going to go from that side 0, we're going to go 29 that way. Okay, so you got to use the inner, let me just get in here. We're going to use the inner degrees. So 29. Okay, so we measured our 29 from that side, and then we're going to draw our construction line. And there we go. There's our construction line, and that is our phi. So that's theta, and this is phi, and that's also 29 degrees. 29 degrees. Okay, so that's 29. That's 29 because it's symmetrical. Okay, now how long is this line? And this is the relative velocity at the outlet. How long is that line? We have to figure that out. Okay, so remember now, there's friction involved, so it comes in at a certain velocity and leaves at a certain velocity. Okay, it loses some of its energy. Okay, because of friction, and they said it's 70 or 0.7. Okay, so where's my notes here? All right, so okay, no, I'll just draw it on here. It's fine. So let's see here. We're gonna do, we know what the relative velocity 1 is, and we know that the relative velocity 2 must be 0.7 of what it was. So it's got to be 30% slower. Okay, so what we're gonna do is we're gonna say VR2 equals VR1 times 0.7. Okay, and so that's going to be 625. So there's 625 times 0.7, and obviously that's going to get smaller. So we got 625 times 0.7, and there we go. It's 30% less. So now it's 437.5 meters per second. Okay, so you can see it's lost some of its velocity. Now we go on this construction line and we measure that off. So firstly, we need to know again how much to measure off. So we're going to say 37,5 meters per second divided by the scale, and we get 8,75. So we divide this by the scale, and then we get 8,75 centimeters. Okay, and that's how long this line must be. So 8, there we go, and that's the outlet. Okay, so I draw it up to that point. Oops, I went too far there. Sorry. So it's from that point, ignore that there. From that point to that point, that is our relative velocity 2. So VR2 equals 437,5 meters per second. And the length of that we measured to be, or we calculated it to be 8,75 centimeters. Okay, so there we go. And then to end off the diagram, we're just going to join that point to that point there. Okay, so let me do that. Where's my pencil? There we go. So we join that, and that is the outlet velocity. Okay, so that is our that's V2, right? V2, and we need to measure that because we don't know what it is. And we're gonna say, what is that? I think it's 4,5 or 4,6. Yeah, 4,6. So that is 4,6 centimeters. And to get the velocity, again, it's just 4.6 times 50. And then we're going to get 230 meters per second. Okay, so there you go. And that is the diagram. To get beta, we just extend the construction line here, because we want to get beta now. Let's see, get this to there. That's beta. We have to use our protractor again. So we put our protractor there, and we measure this way, and that angle is about 69 degrees. Okay, so we measure like that across to that point there, and we see that 69 degrees. Okay, there's our diagram. All right, now remember, just quickly before we end this video, if I make a construction line down like that on that side, and I go on this side here, and I make a construction line down like that, this total length that we measure, so from here to there, that is our velocity of whirl. Okay, that is the velocity that's causing the rotation. Okay, that's our velocity of whirl. On this side here, this is our velocity of flow 1. So from here to here, sorry, from there to there, that's our velocity of flow 1. And on this side, let's do that as well. From here to here is our velocity of flow 2. Okay, so that's very important. That's on the note as well, because you're going to use these values, the velocity of whirl, the velocity of flow 1, the velocity of flow 2, for our calculations. All right, so I hope that video helps.